Hi everyone, and welcome to my video, which is about the Sonogashira reaction mechanism. And I'm Ivor Divenacher, who will be helping you through this very complex and long mechanism. So one thing you need to know about the Sonogashira reaction is that it's got 4 key steps that you very distinctively need to label and separate in your discussion. So I'm going to help you to exactly label the parts of the Sonogashira reaction that's applicable to these 4 key steps. That's what this video is all about. So there's a lot of Sonogashira reaction possibilities. The example that I chose to explain to you the mechanism is the anhydrous copper palladium dual catalyst in alkylation. So basically it means that we have a triple bond that wants to bind to some other ligand, and we have 2 molecules which acts as metal catalyst. They are not one molecule, they're 2. And anhydrous means we don't want any outside environment or moisture to introduce itself to our reaction. And the schematic overview will give you an idea of the roles of each molecule that's going to be in our mechanism. Iodobenzene and phenylacetylene are our only 2 reactants in this reaction. We have a solvent and a base, a dual purpose for triethylamine, and then we have the 2 catalysts here, and you can see this very small molar quantities. That's the indication that it's definitely a cyclic catalyst. We've got palladium, and that 2+ is pretty important because the charge is going to fluctuate as we go along with this mechanism, and it is an extremely important part of the whole discussion. Then we've got copper 1 iodide, and our product looks like this. I did write this name here, but the more commonly referred to name is diphenylacetylene. Alright, I'll repeat. Diphenylacetylene. So that would be more commonly used. I would prefer you using that name. So what you can see from the distance here is that this reaction is basically hoping to get rid of this iodide here and this proton here, so that this phenyl ring can add itself and bond itself to the triple bond there to form this molecule. But you have to go through a lot of hoops and jumps to get there. So the reaction looks like this in the end. This is a preview of the reaction. This is my final slide. I want to give you an idea of where we are heading with it, so that you can get the bigger picture. I know it looks extremely all over the place and quite intense and even intimidating, but it really isn't. Once you understand each step, it is even easy to memorize, and I can promise you at the end of this video you should be able to draw it without even looking. So a tip here: if you do draw your reaction, let's say with pen or on ChemDraw, you need to draw 2 circles which will represent 2 cycles, and you have to make sure that you leave enough open space on all the sides, especially in between the 2 cycles. And you have to make the copper cycle slightly smaller than the palladium cycle, because there's a lot more going on here than here. Which brings me to my next slide. I actually thought it's a good idea to start with the copper cycle, but before I do that, just another tip: make sure that your cycles are in the opposite direction, one clockwise and one anti-clockwise. It would be wise to make it the same as me, the palladium clockwise, because that way you don't have to bother about figuring out everything in mirror image. So here's the copper cycle. We start with the cycle because it's so much easier than the palladium cycle, and for now we forget about this. So there's only three key role players in the copper cycle. We've got one reactant, we've got one catalyst, and we've got one base. And we can discuss the properties on the next slide. Basically, you can read through all of this if you wanted. You can add this to your lab report in the end. But I'm going to just discuss what I think is more relevant for our mechanism. This is an acid, sure, there's acidic proton there, but it is also very electron rich here. There's like an electron density cloud around this triple bond here, and on top of that you got some stabilization going on here, and there's more electron density there. So this is a molecule that's not all that keen to receive more electrons to give its proton away. And then on the other side we have a very mediocre base that's not going to be too basic. It is because of the steric hinderness that's surrounding it with the three ethyl groups. And as such, you're going to need a help to initiate this reaction, and that's where our copper iodide comes in. So what happens when you add the catalyst with the reactant is that it will make this electron dense cloud, like I've said, around it, or in its proximity, and you will have copper being very attracted to that. You know, copper is a metal which is usually Cadianian on its own, and as such it's going to want to be close to any possible electrons it can stabilize with. So it is now a pull and tuck, kinda. Tug and pull, or pull and tuck, how do you even say that again? Anyway, and it is between the iodide and this triple bond, and it keeps these molecules in close proximity to each other. In other words, should this base cause any unstable reactive intermediates, it's not going to matter much because we're in close proximity here, so everything's going to happen very quickly without really causing any complications. So that's the role of the electron density there. And then these three molecules met at some point. And then what happens is we get these intermediates on this slide. The iodide was readily available to stabilize the conjugate acid of the base here, and these molecules are now done with the cycle. They only go out of the cycle. They are so stable and happy, they're just going to be spectators from here on and not going to react any further in theory. On the other hand, we've got a deprotonated acetylide anion, and this is supernucleophilic, and the copper is still somewhere in this cycle here. So it's going to meet up with that copper here. And then when that happens, we have this. This is not a product, but you may refer to this as the product, but not really, of the copper cycle. Basically, this is the intermediate that the copper cycle produces so that it can exchange with something coming from the palladium cycle, and it exchange here. You see? There. And basically it's going to be a trade-off between a ligand and a halide, or a halogen rather, and this will then restore our catalyst here, because look at this. If this is a spectator, then surely it's going to complicate our cyclic catalyst to be restored, right? And we've got copper here. Copper is just going to break off and come back here and form this again. But we don't have an iodide, so the halogen, or the halogen that gets donated from the palladium cycle is iodine ion, and as such the regeneration of this catalyst comes with the help of a palladium cycle intermediate. So moving on. Oh yeah, I forgot to say this. So if you do draw this copper acetylide complex, be sure to draw it more here towards the right top of the space in between the palladium cycle and the copper cycle, because you're going to need space to make the X, basically, sorry, the X for meeting here in the middle. And I forgot to say that this is a sigma bond. Okay, this is sigma bond in between those two. Here is a little bit extra information for your lab report. I'm not going to discuss all of this. You can just, if you want to, pause the video, write this down in your lab report for extra, you know, minimum words you need to add there. So I already explained to you that it meets here in the middle. So this slide is kind of like not needed. Here is it now. It was the iodide ion that was donated by the palladium cycle, and it interacted with this, which gave us another electron dense anion, the same one that is here. And we will discuss this just in a little bit, because I know this is super weird, right? Also, take note that there was some kind of intermediate here, all right? And this intermediate happened to have iodide on it. This intermediate came into the cycle, and it gave its ion, it did give an ion there, and then it proceeded here without the ion. Then this is going to meet up with it and is going to give us something there. Do you see? Okay, so discussing why we have the two of the same molecules. So the reason is the exchange that happens in between the palladium cycle and the copper cycle is an exchange of ligands and halogens. And as such, this would be ineffective as a nucleophile for this reason. Look here, this one could have just taken a shortcut and already took over the job there. But then, if that happened, then our catalyst here at the bottom would not have been restored. With other words, the reaction wouldn't be pushed into the forward direction kinetically. And also, you need two metals to exchange ligands. So what you have here in the intermediate is going to react here is the palladium. Why I keep on saying palladium, I cannot get myself to stop saying that. Palladium, and it's going to exchange something which we now know is the iodide for this ligand. It's going to want that ligand in exchange. Here you go. Here is the full exchange. So take note that this molecule right here is an intermediate. This is not the catalyst that we weighed and measured on a scale and then put into a flask to react. It's not that. This is what is the result of what was put in the flask to react. With other words, an intermediate. It came from, let's pretend our product goes, well, not our product, our real catalyst that we, weigh and so on, comes in here in the cycle, and then it spits something out and it becomes this after a reaction. So just take note that that is not a specific region that we add, it's just the intermediate. Another thing that is very important here is the 2 plus or plus 2, however you want to go about it, that surrounds the palladium there. we are going to discuss it a little bit more in detail, but what you can take note of in the meantime is that we get palladium 0 and palladium plus 2 plus. And they are not the same in terms of reactivity. This is a super stable molecule, and this is also stable. It's not very much unstable, but it's at least more reactive than this. So it's quite important that you have to understand that this palladium right here at this point in time is in its reactive state. Though not super reactive, it's reactive enough. So yeah, it's in its reactive state, the 2 plus. Hold on, I just need to take a sip of water. And here you can see the ligand exchange. There used to be an iodide there, right? Now there is this ligand. With other words, this added itself to the remainder of this. And it made some trans molecule. Look at the phosphine groups. Here is one, and here is one, and they're opposite from each other. And this acetylene and this phenyl is very, it's almost the same thing. And they are also trans from each other. So we've got a trans molecule, which is very important to note, because there's some upcoming steps that is going to dive into great detail on this. So here I have defined for you in terms of structure what transmetalation is. Transmetalation starts here, transmetalation ends here. And it's quite important because in your lab report you don't want to continue talking about transmetalation when you go into another reaction step. You want to be sure to say, all right, now transmetalation stopped, it's done, we're going on to the next step. That's important to distinct between them. Another thing that's noteworthy that I didn't add here, sorry about that, we already know this is the case for this palladium. It is the same for this one. This is in its reactive state again. And on top of that, you can imagine that this part from here to here will have palladium 0. It's in its, well, let me think about that, because there's still a phenol group there. It's somewhere in between. This is what I would draw on it. Hold on. This is what I would draw on it. Let me just erase that. I would say it is pretty much this. Partially positive. Yeah, partially positive because it's got one bond still. Alright, so that's what, let me think about that. Partially, yeah, no, definitely partially positive. So we're moving on to the next step, but this is just for your lab report. You can read what is transmetallation defined in better words than I can put it in maybe, and you might want to add that. And transmetallation is basically an exchange between two metals, like I've said, and you look at the different properties of each metal, and then that will determine how they are going to exchange their ligand or halogen. What you specifically need to look at is how electronegative a specific metal is. We call it the Pauling scale, and you were probably made aware of this in Gen Chem, where you have some arbitrary values to each element on the periodic table that represents how electronegative a compound is. And the rule here of transmetallation is the metal that is the closest to the carbon ligand that it wants to bind with will be the one that binds with it. And because this electronegativity is much lower and further away from that one, this one will be pushed off and sent to bind with our iodide, which will be a 0, I mean a minus at this point. Then moving on, we have a new step, and this is the crucial, I would say, rate determining step. We call this oxidative addition, and it's all this in red. Okay, I'm going to explain it to you from this slide, so it's easier because now it's highlighted. So basically, this is our pre-catalyst. This is the molecule we weigh on the scale, and then we transfer it to a flask or whatever. So this is the product, the molecule that you will get that's already synthesized. And look here, it's got 2 chlorines trans from each other on this molecule, but this you call a pre-catalyst. This is not really truly a catalyst. Why? Because it's participating in a cyclic reaction, yet it's not going to be returned. But in other words, this is not gonna happen ever. Only, oh gosh, sorry about that. Only this will happen. They should make this more user-friendly. So something is going to happen with this molecule, and it's going to make this molecule, and then it will bypass this, and it will shoot, it will go out, it will shoot out here, and it will react here. So in essence, this is our true catalyst. With other words, here it is going to be palladium 0 with 2 phosphine groups attached. Yeah, so this is our true catalyst. It's the same molecule as here. It's only that this is not present there. This is gone. So let's explain to you what is that's going on there, because it's something that you don't really often see. It's my expression on the attraction between the bonds. Look here, we've got benzene iodide joining the cycle as a reactant, and it's going to have to react with a super stable and happy palladium, because when palladium is in its neutral state, meaning it's got 18 valence electrons, and metals love to have 18 valence electrons in their orbitals. All metals is called the 18 electron rule, okay? And I will write here a big 18 so that you can remember it. So when it is in this state, it only has 16, and that means it's slightly more eager to obtain electrons to get back to the 18. This is the perfect state for any complex of any metal, and in our case that's the situation when that palladium is 0. And this is what moves this reaction forward in a kinetic and thermodynamic kind of way. It really pulls everything to here. But the cool thing is there will be another Pd0 here, like I've said earlier. I think I did draw it here, and this also means that the reaction gets moving into this direction. It pulls into that moment when palladium is in its 18 electron valence electron state. Alright, so now that we've covered this, let me just delete this. Oh, I went back instead of forward. Why did I go back so much? I don't know what happened. Okay, here we go, just one more to go. And then, yeah. Here's the 18 electron rule for you in words, should you want to add it to your lab report. And it is a key activating step. It's just what I told you now. It keeps things moving forward. So here we have a new step. Can you see it? Because it's quite sneaky and unremarkable. It's this one here. See the orange arrow? Basically, you can note that this is a trans complex because it's got a phosphine opposite of each other, or if you in terms of where the palladium is centered. And then also, you got the acetylene and you got the phenyl. That's almost the same kind of molecule, right? And they're also positioned trans from each other. But then it goes into a cis formation. And this you call trans-cis isomerization. Let me go to the next slide, which I have the name there. Okay, see, trans-cis isomerization. So, as you know, if you've done organic chemistry, which I'm sure you have, you would know that this is a very unlikely arrangement for any molecule to do because of the repulsion and the steric hinderness of moving a thing so bulky over each other, basically. And then to have these carbon skeletons attract towards each other is also kind of weird, right? So why does it do this? If it's thermodynamically expensive to arrange itself like this, which it is thermodynamically expensive, then why would it? The reason is because it's kinetically favored. This is a phenyl that will bind, that wants to bind back to that acetylene there, and the fact that this cis is now formation is now under some strain means that this bond is more likely to happen, and also because once it breaks off, we have our palladium 0 back, and as I've said, everything will move forward for the reason of this moment and for this moment, and in a way for this moment. So yeah, it will give us our product, because if you remember that we have this acetylene here, phenyl acetylene here, and then we want a phenyl to join or bind to that triple bond, and this is how it does it. The cis formation makes it so much more favorable for these molecules to rather just give up and break up and just form their own thing. And that brings us to more theory, which you can use in your lab report. It brings us to our product. Look at that, so shiny. So this is also a very stable and favored product. That's also something that pushes the reaction forward, and you name this step reductive elimination, which is exactly the opposite of the oxidative addition which we had here. It is because the fact that we eliminate this our product, the palladium is only left with these two phosphine groups. So basically, also because the bonds have broken, it would be back with two more electrons that is in its proximity, and it would have a neutral charge. Let me explain to you this way. There's a 0 charge here, and these aren't really bonds. Maybe I should discuss that first. Well, what's going on when benzene iodine gets introduced in the reaction, the very stable palladium doesn't really want to react. However, the bond between this and this is further apart on the periodic table, and the same goes for this. Iodide and carbon ain't that far from each other, so this bond would break and these two bonds would form, because of the fact that there's a huge difference in all their properties looking at the periodic table. And when it has to use an electron pair to make a bond, it will then go into this state, because now it's got that electron pair less. And the same goes for when it goes into its 0 neutral charge. It is when two things, let's take this for example, it's when these two chlorines, they break off, and then the palladium is also just surrounded by the phosphine groups. So remember, this that I drew here isn't real bonds. That's just an attraction, and it's a tug and pull competition for these attractions to eventually decide which ones get to form as bond with the palladium or the iodide or whatever. So that's how you keep track on the electrons and the charges that you add on palladium. And as such, the molecule went from a 2+ here, let me just do that, a 2+ here to a 0 there. And as such, it was reduced. And this is our whole reaction in the end. It is labeled and color coded for you for your discussion. So I hope this was useful. It brings me to the end of my video, and if it wasn't too painful to watch, please give me a like, because I'm still very new at this, and I hope that I've helped you with your lab report. Good luck on your lab report.